Let's begin. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bohr Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Chayan Sarkar, and he will be speaking on a networking perspective of multi-robot systems and telerobots. Dr. Chayan Sarkar is a scientist at the TCS Research. He received his bachelor's and master's degree in computer science from Jadavpur University in 2009 and IIT Bombay in 2011, respectively. He completed his doctoral studies at the Delft University of Technology, the Netherlands, in 2016. He briefly worked as a researcher at SICS, Swedish ICT in Sweden. Currently, he is part of the Robotics and Autonomous Systems Research area of TCS Research. His research interest includes multi-robot systems, human-robot interactions, and networked embedded systems. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Sarkar directly. Over to you, Dr. Sarkar.
Thank you very much, and thank you for inviting me. Today I'll be talking about mostly about TCS Research or the robotics research activity within TCS Research. And some of these research activities are closely associated with some of the networking aspects. So I'll be briefly touch upon those, though this will not cover a deeper inspection into any of the networking challenges. But the idea is to I'll briefly cover or highlight some of the challenges that we face or a robotics community at large face, and there is scope for improvement there. Before getting into the details, if may not be all of you knowing this, that TCS Research has various research groups, and on the left hand side you can see the various research groups are listed here. I'm part of Robotics and Autonomous Systems. We have labs in different parts of the country. Currently, people from our group, that is Robotics and Autonomous Systems, are part of either in Delhi lab or Kolkata lab or Bangalore lab. Apart from these locations, we have labs in Mumbai, Pune, Hyderabad, and Chennai. We have our social media handles. If you search for TCS Research in Twitter or Tata Consultancy Services Research in LinkedIn, you will find regular updates about research activity within TCS Research. As you can see, our research activity spans across all aspects of computing. So anybody who would like to work with us or collaborate with us are most welcome to contact us. Just a brief outline. This is not something, as I said, going into the details. I'll briefly introduce about robotics research at TCS. Then the rest of the things I'll be talking around primarily my research activities and the communication needs, particularly multi-robot systems and telerobots. So if you look at robots, roughly, if you want to categorize, there are different ways you can categorize robots based on usage perspective. If you try to categorize, there is industrial kind of robots, for example, in manufacturing or in warehouse or food processing, there are different types of robots. Then at the personal space, there are robots, there are robot tutors, there are robot pets. And then at the utility side, there are different robots. You can use robots as guide, a robotic nurse, and so on and so forth. So these robots, depending on the usage, they either work autonomously, sometimes they interact with human, but Nowadays, the robots are also possess some sort of intelligence or cognitive ability to cope with various uncertainties that it may face. So earlier, a robot or a mechanical device were you used to use for one dedicated task with minimal environmental dynamics. Nowadays, robots are there are multi-purpose robots, or the robots, instead of doing only one type of work, they can work in different they at different point of time they can work on different activities, and often they collaborate with other robots, or they collaborate or communicate with human beings. So whenever a robot needs to collaborate with other robots, they need to exchange information, they need to communicate with each other. Similarly, when a robot needs to communicate with a human being, one is natural way of interacting if the human and the robot are at the same place. But there can be telerobots where a human being is in a far location, and the robot in another remote location. So then communication plays a key role in operating these robots, right? So you can imagine communication plays a vital role in such scenarios. More into that, I'll be coming as I move forward. Let me briefly tell about what is roughly what are different robotics activities that are going on within TCS. We started with mostly industrial robots kind of application. You can see different use case of industrial robots. At the left side, the left image is showing a warehouse kind of setup where robots are carrying objects within the warehouse. We all know that different e-commerce companies, they operate a large warehouse where goods movements has to be done efficiently, and they often employ a fleet of robots there, right? Similarly, in packing industry or postal industry, they also use robots for packaging or sorting. At the right side, at the right image, you can see a Tesla factory, an image from a Tesla factory where robots are used to manufacture cars. So you can see these are applications of multi-robot systems, and these robots need to synchronously work on a particular task, right? So they need to exchange information with each other over time. So we started with these kinds of application within TCS, and then it moved beyond these use cases. So if I have to now briefly categorize what are the two areas or two primary areas that our primary focus is, one is multi-robot systems, another is remote assistant. In multi-robot systems, the research areas are multi-robot task allocation. You have seen in the previous image that when in a warehouse, large number of robots are operating simultaneously to carry objects from one location to another location. So carrying object can be treated as a task. So which robot should do which task and in which order, that is decided based on this. So multi-robot task allocation actually does that. Similarly, multi-robot coordination, you have seen that robots are synchronously packing, or they synchronously doing manufacturing. So depending on the application, the level of coordination is different, but multi-robot coordination is one of the active area that we work on. Ambiguity is one of the challenge that we participated along with team from IISc actually. So we were in top 10 in the final round of this challenge. In these areas, we do not only ground vehicle, but drone related activities, that is drone navigation, drone control. SLAM is simultaneous localization and mapping. These are active research areas. Then cloud robotics is another area where we provide robotic solution as a service. You think of this as a centralized service provider that you can take to a industrial setup where the robots are connected with the cloud-based system. The robots are instructed and controlled by this cloud-based system, whereas these cloud-based systems provide a dashboard to the user, and it can run different kinds of optimization. It can provide a digital clone of the entire setup. So that is another area that we are working on. Robot picker, or particularly the system that we have built within TCS is called Pal Picker for a smart warehouse. That is the hardware. So this is the hardware that TCS has built. This can be used in different warehouse or parcel sorting centers. In the remote assistant setup, we have a robot or a solution for telepresence, where you can attend or discuss with a remote set of people with a robotic hardware, with a mobile robot. You need not travel to that remote location, but through that robotic platform, you can log into the system and interact with the environment and with the human being there. Similarly, teleoperation is you have a robot with some manipulator, and you can control the manipulator from a distant location. On teleoperation, we have again participated in a challenge called ANA X Prize, and that is again jointly with IISc and Hanson Robotics. We qualified for the semi-final, but we could not qualify for the final round. But at the end, we had pretty good experience in working in those challenges. So let me show you this video to roughly summarize what I said and what TCS is doing. This is the telepresence robot that you can see on the screen. Somebody remotely logged into the system and controlling the robot to visit within an environment. So it can be utilized for remote facility visit, remote lab visit, or remote, let's say, production plant visit. Somebody can remotely inspect a high precision instrument as well. Some other things in terms of robot interacting with human being giving instruction using gesture, and robot is following that. Other thing is this telepresence system can actually track human voice and who is the speaker, and it can orient accordingly. And the Pal Picker system, this is the robot that we built. The other robot, that is the platform, is called Double 3. We bought it from a third-party vendor, but this hardware is our own hardware. Now, I personally work on these two areas, multi-robot systems and human-robot interaction, and I'll be briefly talking about these areas and highlighting some of the networking aspects of these areas. So this multi-robot systems are used in different industries. As I mentioned, warehouse fulfillment centers is one of the primary application areas. This is an Amazon warehouse where these robots are called Kiva robots, used to transport objects from one place to another place. You can see the objects, different objects are stored in the racks, and when there is a customer order, the system knows that this object is stored in this rack. So a robot is assigned this task. Robot goes and brings the rack to a human worker, and the human worker picks up the object and puts the addressing stamp and then ship it to the customer, right? We'll just skip this. So these kinds of robots are used for almost decades now, or more than a decade now. But these robots had certain limitations. One of them is, even if only one object is ordered from the storage racks, the robot has to bring the entire rack, right? The reason is the robot cannot pick, or there is the manipulator is not suitable to pick different types of objects. You can train a manipulator, or you can write program to handle a particular type of object. But in a warehouse, you can imagine the types of objects are very different from each other. So the manipulators were not, or the technology was not matured enough to handle individual objects separately. So the solution was to bring the entire rack. That was the system they were using. So that's why they wanted to change this, and they have thrown this Amazon Pickup Challenge, where the idea was to pick individual or different types of object correctly. So this is one of our robot. Of course, the hardware we bought it. This is KUKA ARM, and we wrote the software stack to handle different types of object. The suction type gripper actually, so through the camera we identify what kind of object it is, and the suction type of gripper positioned properly and applied proper suction force to grip the object. So that was the solution. It sounds simple, but it took quite a lot of effort to build this. So we participated in this challenge in 2016. Initially, so it was a joint team of IIT Kanpur and TCS. Initially, after day one, we did quite well. In the leaderboard, we were at the 5th position on the left-hand side, as you can see. But at the end, we didn't do that well. In that year, team from TU Delft actually won the competition. I graduated from Delft, so I'm certainly proud of this. In 2017, though, our team, IIT Kanpur and TCS joint team, performed really well. At the end, we secured 3rd position in the pick task. And if you look at the final score on the right-hand side, our team did better than a joint team of MIT and Princeton. So something to be proud of again. Now imagine this scenario where what used to happen earlier was that starting from the origin, or starting from the packaging location, a robot goes to the task 1 location, picks the entire rack, and then brings the rack to the origin, and then goes for the next task. Now what happens, robot can pick individual objects. So on the right hand side, you can see robot first goes to the task 1 location, picks the individual object, not the entire rack. Then it goes to the task 2 location, then picks the second object, and then it can come back to the origin. Or it can go and pick multiple other objects and then come back to the origin. So this actually depends what is the capacity of the robot and what is the weights of different objects in a task, right? So this problem can be mapped to a classical computer science problem called capacity constrained vehicle routing problem, or CVRP. This problem is known to be NP hard, so there is no optimal solution available. There are certain exact algorithm exist, but that is only for up to 100 nodes or 100 tasks. Whereas we have a problem where we have thousands of tasks and hundreds of vehicles or hundreds of robots, right? So there are heuristics algorithms, but again, they are not scalable for such a problem, such a large problem. So we worked on this and we have come up with an algorithm called NCAR. We have compared it with a Google Word toolbox. This is an optimization toolbox. On the x-axis, you can see the number of agents or number of robots, n, and number of n is the number of tasks and k is the number of agents. On the y-axis, you see the total cost of the solution or the total distance traveled by all the agents to complete all the tasks. So the lower the cost, the better the solution. When the number of agents and the number of tasks are relatively less, our solution is at par with our tools. But when the number of agents and number of tasks increases, our solution performs significantly well. And just to demonstrate you this, how the system works, imagine these are two warehouses where these rectangles, smaller rectangles are the storage locations. These four colored circles are the robots. Initially, they were at the packaging location and then they went for pick. So in one round, a robot can pick multiple items depending on the capacity and weight of the tasks. It comes back to the packaging location, drops those objects, and then goes for the next round, right? So in the left-hand side, you see the algorithm task allocation based on our algorithm, and right-hand side, state of the art. So you will see that at the end, our solution finds the does task allocation in minimal cost, whereas that state of the art takes a bit more time. So for such a system, so now you probably have this idea that in a multi-robot system, you need a certain level of coordination and information exchange among the robots. So if you think a scenario where you have tasks, and if the tasks are not known, the agents are freely moving within the field. They are discovering the task and they have to advertise about the tasks, and every agent should know, okay, this is the task, and then who should do the task. Some task allocation has to happen on the fly, and then that agent starts working on that agent on that task, right? So the communication plays role in terms of task information dissemination and task allocation. And at the end, after the task is completed, status update is also required, right? Now, sorry. Now, the situation that you have seen earlier, that warehouse, there the networking challenge may not exist anymore, because probably you can, in an indoor setup and an infrastructured setup, you can deploy a couple of Wi-Fi routers to cover the entire area, because this is a managed setup. So you can plan your network, and the robots can directly update a centralized server. The central server can manage all the task allocation and everything, right? But when you have outdoor application scenarios, for example, search and rescue, exploration, or even agricultural applications, you need not have communication infrastructure all the time. So there the robots has to manage on their own. So you need to set up, so the robots can form ad hoc networks among themselves. So there different communication challenges lies, right? Swarm robotics is another application area where communication certainly plays a role. In swarm robotics, the robots are typically much more miniaturized than those robots that you have seen in let's say Amazon warehouse. So they have low energy budget and low I mean their form factor is also smaller. Information exchange certainly plays a role because they actively coordinate among themselves. But the question is, how should they exchange information so that there is no not much overhead in terms of energy, right? There are different approaches where people don't use RF based communication but other means of communication, but RF, energy efficient RF based communication certainly can be a big changer, game changer in this area. And another point here is, because of low reliability of typical communication techniques employed in swarm robotics, they are not employed in industrial setup. But if we can improve the communication reliability, probably it can be an alternate solution. So as I mentioned, in outdoor setup, there are many application areas of multi-robot systems, and there much harder communication challenges are there. So we have worked on such problem where we don't use infrastructure based communication setup, but an ad hoc network where multi-hop communications are employed. And the idea is to use miniaturized robots with energy constraint and energy and memory constraint. The application was that a bunch of robot forms a group and maintains a formation. In this case, we have tried to maintain a concentric circle, and the robots, while moving, they exchange information with each other. Now, here, one of the thing is not only the energy constraint of message exchange, but the message exchange has to be in real time, so that they can maintain their positional synchronicity, right? So for this, if we look at the existing communication challenges, the predominant ad hoc networks use asynchronous mode, and asynchronous protocols they often suffer from real-time guarantee, a lot of packet loss, increased latency. So those issues are well known in asynchronous communication mode. So we try to develop a synchronous transmission based communication protocol for multi-robot system, so that the control informations can be exchanged efficiently and reliably. So we have extended the work of concurrent transmission based network wide flooding. Glossy is one of the well-known protocol in this area in wireless sensor network domain, where where sensor nodes actually exchange information with each other using the effect of concurrent transmission. So they use constructive interference, the idea of constructive interference, when multiple nodes send same data at the same time, the packets collide constructively or the data collides constructively, so the receiver can actually decode the packet. So that is the idea behind constructive interference, and we have utilized that the mechanism in terms of exchanging information, control information with different robots, and we achieved a high synchronicity in terms of formation maintenance. If you are interested, you can look further in this paper. This is a joint work between TCS and IIT Bhubaneswar. Now, moving to the other part of my work, that is human-robot interaction. robots are being used in industry for many years. At this point, maybe I should pause a bit. If anybody has any quick question, I can answer. Otherwise, I'll just continue. Hello? Am I audible?
Yes. So
Okay.
are there any questions?
Fine. Maybe I'll continue. If you have any question, you can ask at the end as well. Okay, so we have seen robots are being used in production lines for many years. But nowadays we see more robots in our surroundings. And when there is a robot in our surroundings, there is a scope for interacting with human beings. So human robot interaction is a major research area within robotics for last 2 decades at least, or last 3 decades, I would say now. So there are different ways to interact with a robot. Spoken language is certainly one of the ways, but gesture based interaction is another common way to interact. Now, the different modalities increase complexity in a robot's operation, or there is a new kind of algorithm there on the robot. So keep this in mind, because I'll come back to this point. If you want to interact with a robot using spoken language, then that means the robot has to have algorithm, or nowadays deep learning based or neural network based model for spoken language understanding. So you need an ASR, automatic speech recognition system, for that. Similarly, if you want to interact using gesture, then the robot should be capable in terms of identifying the gesture. So a vision model is certainly required. And apart from that, if the robot is mobile, then the robot requires capability of navigation, right? So obstacle avoidance, for example, map building. So all these capabilities are required. A bit more details towards the HRI scenario. What happens? Let's say you have a robot and you want to use it for different tasks. You want the robot to do certain tasks on your behalf. So you can interact just giving some instruction in natural language, and then the robot not only translate the audio into text, or that means the robot not just understands the audio, but you also need to understand the semantics of the instruction. That is, what is the task? Excuse me. So if you say, can you go near the vending machine in the hall, the robot has to understand that what is a vending machine, what is a hall, and this is a task where the robot has to move to the hall and near the vending machine, right? So let's say robot understands that, and then it moves to the hall. After reaching the vending machine, it has to identify where exactly is the vending machine, because that information might not be known beforehand. It roughly knows where is, or it may be knowing where is the hall, but not exactly the location of the vending machine. So after reaching the near the vending machines, it see there are 2 vending machines. So and at this point it is unsure which vending machine it should go. So it asks which one, right? Or I see a blue and a red vending machine, which one you are referring to, right? So and the human being responds that the red one, and then the robot understands what is intended. So if you now think, the robot has to understand that what is the task, and while doing the task it can face some sort of ambiguity. In this case, the ambiguity was, it was not clear which vending machine, whereas there are 2 vending machines or more than 1 vending machine. So it asks a suitable question. So robot has to have the capability to understand and ask, raise a question depending on the situation, right? So that leads to this challenge of task identification and task planning. So human instruction by default is ambiguous because we don't always follow a very human language is not a formal language, right? So it is not a very structured language in that sense, particularly English. And we don't always explain everything explicitly. We don't say everything in full sentences, right? So that can lead to ambiguity, and that can lead that the robot may fail to understand something. And as I also shown earlier, that even if initially the robot understood something and build an hypothesis and start working on it, then while working it can again face some difficulty, and that time it also need to engage with the human being. So to facilitate a robot for such a setup, we have developed TCAR, or Task Conversational Agent for Robots. The idea is it has a dialogue engine that helps the robot to raise a question whenever required, and also a task identifier module which identifies task from the natural language instruction, and a plan generator. This is a high level plan generator so that the robot can execute the task. So we have published a couple of papers. I'll not going into the details of these work. If anybody is interested, you can look at these papers. Now, roughly how it works, we have trained models, machine learning, through machine learning. We have trained the models. We have actually trained a conditional random field based model using a tag sentences, a set of tag sentences. So this sentence bring me the pen from the table. The model actually predicts this is a bringing kind of task, and we have defined templates for a bunch of tasks because obviously robot has a limited capability. So that kind of task a robot is capable to do, we have defined a template for that. A template actually contains the task parameters. So a bringing kind of task actually requires an object that it has to bring, a source location, and then probably a destination location. So destination location is optional in that sense. If I just say bring a pen, then the destination is where I am currently standing or sitting, right? So the model actually first predicts what kind of task it is, and then it also predicts the task parameters. If it fails to predict what kind of task it is, or fail to predict some of the task parameters, it asks questions, right? And once it understood everything, it generates a plan and the robot executes it. Take a look at this example. The instruction is take the book and bring it to the desk. So the robot understood that the first one is a taking task and then the bringing task. For the taking task, the object is book, but the source location is not available in this instruction, right? For the bringing task, the source, the object, and the final location is available. The object is referred, it is through co-reference resolution. The word it actually refers to the book, which is actually the object. So one information is missing. The robot asks a question from where should I take it? The human response, take it from the table. So all the informations, required informations are available. So a plan is generated. Asking the question certainly depends on the context. So take a look at the first scenario on the left hand side. If I say bring me the pen, and so in that case the source location is not available with the robot. So the robot doesn't know the source location of the pen. So it asks, where can I find it? Now look at the right hand side. First, I say pick up the pen from the table. So there is a pen in front, assuming there is a pen in front of the robot on the table. So the robot picks up the pen. So the robot actually possesses the pen. Now, if I just say, bring me the pen, in that case, robot already has the pen, and that means robot knows the location of the pen. Or location actually not required. It is already with the robot. So it need not ask the question. It just executes the task. So what is our dialog policy? We actually start predicting the task type. If we predict the task type, this is again a probabilistic model. So with the task prediction, the type prediction, we also predict the probability of this prediction, right? So we also, so if the probability is too low beyond a threshold, we ask question. If the probability is high enough, then we don't ask question. If probability, then actually the probability is generated for a bunch of tasks, and we rank them based on probability. We first ask the question based on the highest probable task. If the answer is positive, then that is fine. If not, then we negate that task and then predict again. And then if the next task has high enough probability, we know we need not ask further question. Otherwise, we again ask question. So task prediction and robots execution, actually we experimented with a bunch of users. We have developed this use case scenario where this is a on the right hand side, you can see a floor plan of a meeting room kind of setup. This room has a table, 6 chairs. This larger rectangle is a table, and there are 6 chairs. And then there is a display screen. There is a meeting room door. There is a front door. Initially, this red dot is the robot. Initially, the robot was at the charging dock. And when the robot is asked to go to the door, robot was not sure which door you are referring to, because there are 2 doors. So robot asks which door you are referring to. Then if you clarify that it is the front door, the robot moves to the front door. Then you say, you give it an instruction that turn on the display, robot goes to the display and turn it on, so on and so forth. So this kind of setup we have, this is a simulated setup, right? We have developed to do some user study in terms of understanding how efficient our system in terms of understanding task, resolving ambiguity, and resolving ambiguity with minimal question, whether question framing are suitable for user understanding or not. And then we understood that user face different kinds of difficulty in understanding a robot's response, or the user felt that the robot cannot understand what the user is saying, and so on and so forth. Let me just show you a actual video where we have developed this kind of system with our robot. This is our telepresence robot. I'll just pause it here. This is during pandemic, so the robot is in one of my colleagues' home. I say the robot, can you bring me the red water bottle from the dining table? Now assume the robot already knows the location of the dining table. So the robot moves to the location of the dining table, is moving to the dining table. So after reaching there, after reaching there, it looks at the scene. So it analyzes the scene and it identifies a number of objects. So the initial instruction was to get the red water bottle. It could not find any in the on the table. So it asks a question, in this case, a suggestive question. I say yellow bottle, should I bring it? Right. So depending on user response, it can continue the task or it can abort the task. But the robot understands the scenario and it asks, depending on the scenario, it asks question. Now, think of this setup. To build such a system, what do we require? Right? It requires ASR, a model for audio to text conversion, a model for task understanding, a model for task planning, a model for question generation, and object detection, navigation. So there are large number of algorithms that has to run on the robot simultaneously. Now, you cannot just have a very powerful computing device. Well, nowadays robots have a lot of computation power, but still there is limitation due to the form factors, right? So you cannot have a very powerful machine within the robot to host a bunch of algorithms on the robot. And in future, if you want to add one more capability to the robot, how can you do it if you have memory crunch and resource crunch, right? So can I offload this computing capability to some of the computing power or to a cloud, right? And will that hamper my real-time responsiveness, right? And through our user study, we have seen real-time response play a major role in terms of acceptability towards the robot or usability of the robots. If the robot responds, if it is just a toy and you just use a robot for once or twice, it doesn't matter. But if you use it day-to-day basis, or continuous basis, then real-timeness plays a major role, right? So this is certainly an issue, and depending on where the robot is hosted or what is the application, there is certain concern in terms of data privacy, right? So if you offload the computing to a cloud, the robot just collects data and sends the data to the cloud, and the cloud does all the computation and sends the result, then there is this concern of privacy. So how can we handle such a scenario, right? So edge computing can be a way forward to this, and we actually employed an edge computing setup in our system that you have seen. So this is the network architecture that we have used in our robot setup, where you can connect with the robot from a, let's say, browser of any device. So this left hand side, the master, you can see this is a WebRTC client, or basically a browser. Through that browser, you can connect with the robot on the right hand side, and then the robot is connected with a robot edge, where we host a bunch of AI algorithms, and it is within the vicinity or in the same local area network of the robot. So the network latency is less, and it is easily customizable. You can, it has relatively more computation power, so it can host large a number of computation, a number of algorithms, and you can extend it for newer feature in future as well. We have also published a paper in ComsNet. If you are interested, you can look at the further details here. I'll just end the talk with this poster. We have actually had a trial with Airtel regarding 5G for a remote robotic operation. where using the 5G network, you have interacted with a remote robot for a different robotic operation. You have to keep in mind that there are different types of multimedia stream, simultaneous stream you have to exchange between the remote user and the robot. That is not only audio, video, but sometimes text, and certainly control commands. And those control commands need to have very low latency. So certainly 5G can play a role where 5G is available, but there are certain scenarios where, again, infrastructure may not be available. Tele robots may not be the use case, but the multi-robot systems in outdoor setup that I have mentioned, there 5G can play a role, but many times you may need to use ad hoc networks as well. So with this, I would like to conclude the talk, and thank you very much for your patience. And certainly, I would like to thank some of my colleagues within TCS and Dr. Sudipta Shah at IIT Bhubaneswar. So the work that I have presented, it is in collaboration with them as well. So thank you to them as well.
Thank you, Dr. Sarkar, for an interesting talk. There is a question from Dr. Pavan. Let me read the
Yes.
question. As you have said, English is less structured than many Indian languages. So have you tried NLP-based robotics using Indian languages?
No, so far I haven't tried any Indian language, and I just tried with the English only. Hello? Hello?
Yeah.
Yeah.
So I hope that clarifies that question. So we can take a few more questions now.
Yeah, certainly NLP I have used, but it is nothing but NLP, but it's only for English. Yeah. That would be an interesting area to look at other Indian languages. There are enough challenge to solve in English already, so I'm trying to resolve those first.
Dr. Chen, I had one question related to this application of ML and NLP for training this. So, like for example, image classification or like image-based identification. The robots need kind of training beforehand for doing this, or they're kind of primed with some model which gets fine-tuned on the field?
This is a pre-trained model in sense, but this is before deployment, we certainly fine-tune based on the objects in the environment. So we take a general purpose model. I don't work on computer vision, so I take a model that is trained on, let's say, visual genome, that is, let's say, a model that can detect thousands objects, 1,000 different types of objects, and I fine tune it with the particular type of objects that is available in my environment before the deployment. And after deployment, I don't do any fine tune as such. But yes, if I see there is a misdetection due to whatever reason, there is certainly scope for fine tuning. And probably what you are referring to, that is continuous learning, that is certainly a way forward, but so far I haven't done that.
So what's the current state of the art in terms of the computational abilities available on these portable robots, and like computational in terms of general purpose computer as well as some dedicated, say, TPU kind of chips or graphics chips? And
yeah, so the platform that you have seen that we have, this one has this one is without any GPU and very low memory capability. I think only 2 GB memory. There are robots where you have let's say Jetson in it, but still again, even if it has 16 GB memory, you can, if you look at any state-of-the-art ASR system, and those models are, let's say, easily close to 1 GB. And then you have one dialogue engine, let's say there is BERT for different NLP tasks, and that is again another 500 MB. And if you combine it with different activities, for example, task understanding, dialogue generation, then it becomes multiples of GBs. So it easily eats up all the memory of the robot. These are only these part, but again, you need memory for navigation task, map building. So that is the challenge. I hope I answered your question.
Yeah, that is very informative. So sorry, one more question. So currently you haven't faced a need to move some computation on the cloud, and everything has been done on the device itself, is it?
No, by device means nothing on the robot, almost nothing on the robot, very minimal computation on the robot, most of the thing on the edge. So not on the cloud, not on the robot, but on the edge device. So we keep a desktop or laptop in the office, and most of the computation is on that device. Cloud is again that's the privacy concern. We cannot upload our data to a cloud, at least third-party cloud.
And what is the way you ensure the connectivity with the edge device, and also reducing the latency between the robot and the edge device?
Well, it is in the same LAN. So there is until and unless it is complete blackout or something wrong with the, let's say, router, the connectivity is there. So that is one of the thing. But we so far we haven't employed anything fancy or any reliability aspect from the communication side in that sense. We just relied on WebRTC, and let's say I think WebRTC works on top of TCP. So we relied on TCP.
Thank you so much.
Yeah.
Are there any other questions? If there are no more questions, let's end the session. Once again, let's thank Dr. Chayan Sarkar for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the webpage. Thank you and have a great evening.